We've looked at the building blocks of life, and we've looked at some of the environments in which life might have evolved. But one thing we've assumed throughout this is that life is based on carbon and it uses liquid water as a solvent. Let's revisit that assumption and think about whether there are other plausible alternatives that have been considered by astrobiologists. First of all, we've said that life is based on carbon, and what that means is that the molecules of life have carbon as their backbone. Here are two examples of molecules. Methane, which has a single carbon atom and 4 hydrogen atoms, a simple compound produced by life, but still based on carbon. And on the right-hand side there, the much more complex molecule of deoxyribonucleic acid, or DNA, which is also carbon-based. The molecule is constructed around carbon atoms with other atoms attached to it, such as hydrogen and nitrogen and phosphorus and oxygen. These are carbon-based molecules, and all of our molecules are built up in the same way, using carbon as the basic building block of these molecules. What are the reasons why carbon is such a good atom for forming molecules? Well, one reason is it tends to form bonds with other atoms that are similar in energy. For example, it can form bonds with hydrogen, nitrogen, oxygen and phosphorus. And the reason why it's important that those bond energies between carbon and those other atoms are relatively similar is it means that carbon can move around those different atoms, essentially exchanging them and forming different chemical compounds. It can break a bond with one atom and form a bond with another type of atom without needing much energy or without giving up much energy. And that creates a great versatility in the sort of chemical compounds that you can form. Another reason why carbon is so favoured is because once it does form a bond with these other atoms, those chemical compounds are quite stable. So the result of this versatility of carbon being able to bond with other types of atoms and the stability of the resulting bonds and molecules is that we can produce quite complex organic compounds, such as this DNA molecule here. One alternative that has been discussed by astrobiologists is silicon, and silicon-based life forms have been a favoured alternative for science fiction writers and also in films as well. Here's a rather interesting speculation from H.G. Wells in 1894, and he says, "One is startled towards fantastic imaginings, visions of silicon aluminium organisms, why not silicon aluminium men at once, wandering through an atmosphere of gaseous sulphur, let us say by the shores of a sea of liquid iron, some 1,000 degrees or so above the temperature of a blast furnace." But silicon has some major disadvantages. For example, it forms very stable chemical compounds with oxygen. In fact, you can see these compounds by looking out of your window and looking at rocks. Rocks are silicates, where essentially these are compounds where silicon has bound with oxygen to produce very stable silicate minerals. One of the best known examples is quartz. So on any planet where there's oxygen lying around, it will tend to react with silicon and form these silicate rocks, these very stable compounds that really prevent silicon from engaging in other chemical compounds that might be of interest to astrobiologists as plausible building blocks for life. Of course, we could imagine planets with very, very low concentrations of oxygen that free up silicon to get involved in other types of reactions. But it seems that silicon has too great a propensity to form reactions with tiny amounts of oxygen and form these stable silicate compounds for it to be useful in the origin of life. Another problem with some silicon compounds is they're very reactive. For example, here are two simple molecules, one of which is the carbon-based molecule methane, and we know that we can ignite methane, we use it in our gas ovens. And on the right is the corresponding silicon compound silane, which spontaneously ignites at room temperature. It's a very reactive compound. And that doesn't mean to say that life could not use these compounds on a planet where temperatures were much cooler. Chemical reactions might occur much more slowly and deal with some of the problems with these highly reactive silicon compounds. But nevertheless, this might be one disadvantage of some silicon compounds on a planet like Earth. What about elements other than silicon? Well, if we look through the periodic table at other possible elements that we might use as building blocks for life, unfortunately they don't fare much better than silicon. For example, gases like helium and neon are too inactive to be the basis of chemical building blocks for life. Oxygen, nitrogen, boron and other types of atoms have a limited number of bonds to other atoms and therefore are not going to form the complexity of compounds that we associate with carbon. And Elements like magnesium, calcium, potassium, sodium tend to form ionic bonds. It's difficult to form bonds with many elements in the same way that we can do with carbon compounds. And so as we look across the periodic table and we look at the advantages and disadvantages of different elements, what we find is that carbon really comes out on top as the best element to form stable, complex, and highly diverse molecules. Life also needs a solvent in which to carry out its chemical reactions. And for life on Earth, that's liquid water. Water has many advantages as a solvent for life. For example, it readily dissolves many chemicals, making it possible to carry out chemical reactions. Another intriguing advantage of water, which some people have said is necessary for life, is that when it freezes and becomes ice, it floats rather than sinks. And as a result, life, like these fish, can live under a lake that has a frozen surface. It's speculated that if life used a solvent that sunk when it became solid, then lakes and ponds would simply freeze through completely and prevent life from inhabiting the surface of a planet. Well, of course, we can argue about whether that's true or not, but it is an intriguing property of water that is very beneficial for life living in cold environments. Water also has a very wide temperature range. We find liquid water in the polar regions, and we find liquid water in boiling hot volcanic springs. And this wide temperature range allows life to carry out chemical reactions in many diverse environments on the Earth. What about other alternatives? Well, one alternative that has been favoured by science fiction writers and even scientists is ammonia. Ammonia is interesting because at low temperatures it also readily dissolves many chemicals, and it could potentially allow for ammonia-based bonds between chemicals similar to example for amino acids, and some people have proposed primitive protein chains made from ammonia-based chemical reactions. Problems with ammonia are that it has a very narrow temperature range. It's only liquid from -78 to -34, but perhaps that's not a problem on a planet where there are large surfaces in which these temperature ranges are met. And also it sinks when it freezes, meaning that in bodies of liquid ammonia, when they become very cold and they become solid, they would freeze through completely. But how do we know that there aren't life forms that adapt to surviving for long periods of time in frozen ammonia and thawing out when the ammonia is melted again? Of course, these are speculations that we can't address. There are other types of solvents that have been proposed for life as well, such as hydrogen fluoride. Hydrogen fluoride, when it's a liquid, has a very wide temperature range from -83 to +20 degrees centigrade, and it also dissolves a wide range of substances. The problem with hydrogen fluoride is that fluorine is quite rare in the universe. It's 100,000 times less abundant than oxygen necessary to form water, and it's rather aggressive at destroying organic compounds. So on the face of it, liquid hydrogen fluoride also doesn't look like a particularly good solvent for life. It's interesting to observe that our apparently narrow view of life is actually consistent with what we see in the universe. Some people have said that our idea of carbon-based life forms using liquid water is just a very narrow, Earth-centered view of life, and that on other planets we would expect to find life with entirely novel biochemistries, almost unimaginable to us. But in fact, when we go to other planets in our solar system, we don't observe unusual life forms. For example, on the surface of Venus, that's 464 degrees centigrade, we don't observe strange silicon-based life forms using some unknown solvents. We observe what appears to be a lifeless surface. And so it seems that our prejudices about carbon-based life using liquid water may not be so far from the truth as a plausible view of how life might be constructed through the rest of the universe. But a question that does face astrobiologists nevertheless is, are there other biospaces? Our biospace, based on life using carbon as a building block for its molecules and liquid water as a solvent, might just be one biospace. Are there biospaces using, for example, silicon-based life forms in liquid ammonia? Are there biospaces that use carbon-based molecules in liquid ammonia? A future challenge in astrobiology is to really determine whether these speculations about other types of chemical compounds, silicon-based compounds, other types of solvents like ammonia and hydrogen fluoride are really plausible, and whether they really do occur on other planets or whether they are just fanciful ideas of science fiction. So what have we learned in this lecture? Well, we've learned that carbon is the most versatile element for building molecules, at least as far as we can understand based on our current knowledge of chemistry. We've also learned that water is the most versatile and useful substance for doing chemical reactions. We've learned that there are other alternatives, such as silicon as a basis for molecules and ammonia instead of water. And we've also learned that the fact that silicon, ammonia and other compounds seem less favourable than carbon and water as a basis for life doesn't rule them out. The carbon-water biospace seems to be the most plausible or likely to be the most common architecture for other life, but as astrobiologists we should keep an open mind. There may well be other planets out there, perhaps rarer than the Earth, in which these alternative chemistries are being experimented with as the basis of life.